Good afternoon, everyone. My name is Constantine Tsang. I'm the Deputy Press Officer for DPS, and I welcome you here for the Tuesday press conference of the 48th DPS conference and the 11th EPSC on today, Tuesday, October 18th, 2016. We have an amazing lineup of new results from the New Horizons mission. Before we talk about that, I'd like to just take care of some housekeeping notes. First, for the audience, if you could mute your phones and make sure they're off or silent, that would be greatly appreciated. Second, if you could keep your applause to yourself at the end of each talk, that's also much appreciated. And finally, there's a press release that comes out with this press briefing that will appear on the nasa.gov website, so you can refer to that for further information. We have 5 people on the panel, as you can see, and I'd like to introduce them to you right now. We have David Schurr, Deputy Director of NASA's Planetary Science Division, Alan Stern, the Principal Investigator of the New Horizons mission. They'll both make some brief comments before the start of the main press briefing. We have Bonnie Buratti, NASA's Jet Propulsion Laboratory, Alan Stern, Southwest Research Institute, Ross Beyer, SETI Institute, and NASA Ames Research Center. Last but not least, Amanda Zangari of Southwest Research Institute. And with that, I'll hand it to David. Thank you.
Good afternoon. Since July 14th of last year, the New Horizons mission has continued to bring down exciting new science, which we'll hear from the team today. Just a couple brief comments. The spacecraft continues to do well. The systems and instruments are all performing as expected. The mission will complete its primary phase. The last data from the Pluto encounter will be downlinked as of Sunday, if everything remains on track, which for NASA completes our primary mission, but we have extended the mission. We conducted our senior review earlier this spring and have approved New Horizons for its extended mission to visit the Kuiper Belt Object 2014 MU69 in January 1st of 2019. So we've got a mission that has been approved that'll carry us through 2021, keep these guys gainfully employed for quite a while. So we've got an exciting mission, continues to work well, and look forward to hearing from the science.
Well, thanks, Con, and thanks, David, for getting us kicked off. For those of you who are here in Pasadena and attending the Division of Planetary Sciences meeting, you're hearing lots of Pluto results. You know, David just mentioned that the data is all going to be to the ground by this weekend. That's been a 16-month process, but what rains down are only ones and zeros. And even what comes out of our data reduction pipelines is just raw data that requires the work of human beings in order to interpret. We have over 40 presentations or posters being given to DPS with early results. And I have to tell you, during the entire 16 months when new data sets were landing several times per week, I think we often felt like doctors in an emergency room who were just triaging patients one by one and stabilizing them as quickly as possible to see what was in those data sets. The early results from that process are what are being reported at DPS, and additionally, some of the most interesting highlights, particularly for the public, we think, are going to be presented today in the next 4 briefings. But the hard work of really understanding the Pluto system is going to take years. It's much more complex and nuanced than we ever expected, and we're happy about that. And we hope that from the sampling of results that we discuss in this press conference this afternoon, that you'll agree with us and that you'll continue to come to New Horizons sessions and New Horizons press conferences as we make sense out of all that data that we collected and now have on the ground here on Earth. Thank you. Bonnie?
Okay. Thanks, Alan, and thanks, everyone, for coming. Well, we almost have all our data down. The team over the last year has been working on the data that we already had, and we've kind of moved from pretty pictures to the hard work. And I'm going to be talking about some of the hard work we've been doing and what I think is a pretty amazing outcome of that hard work. So we saw that pretty picture looking back on Pluto right after the encounter, the amazing glaciers and the mountains and the haze. I think Andy Chang has counted 18 haze layers. But we've also been doing some hard work. One of the questions we've been trying to answer is, how reflective really is Pluto? So we've been doing the work of trying to figure out how it scatters light according to the angle you're looking at. And we've produced this map. The GGI team, Geology and Geophysics team, has produced this map that shows the albedos on Pluto if you were looking kind of just straight at it. So these are true reflectivities. What fraction of light is reflected from the surface of Pluto? And we found this amazing thing here that in Sputnik Planitia, the informal named Sputnik Planitia, right there in the middle, the heart of Pluto, it reflects nearly 100% of the light falling onto it. It is extraordinarily bright. But the other thing we found is if you look at the dark regions, which are shown here in blue, in the equator, the reflectivities are more like about 10%, even as low as about 8%. It's quite dark. So we tried to figure out what other objects in the solar system have this kind of behavior. So here's a little graph we put together of other icy bodies. This is the compendium from NASA's missions from the last, really, 30 years, starting with Voyager on up. So on the left there, we have Pluto. This is the maximum reflectivity at the top in blue and the minimum reflectivity on the bottom. So at the top there, 1 means it's like bright, freshly fallen snow. I know we're in California, but sometimes in the mountains we see snow. So Pluto has this amazing reflectivity of about 100%, but it also has these this dark equatorial region where it only reflects about 8%. So if you look at Enceladus, now this is from Voyager and Cassini results, it's also very reflective. It reflects about 100% of the light falling on it. Those are results from Cassini, recent results just over the last 10 years of the mission. Triton, which we thought Pluto was like, doesn't have these kind of reflectivity variations. Europa, about the same. The body that Pluto looks like, it turns out, is Iapetus. This is a strange, a very weird moon of Saturn. This is, on the left, we see a Cassini image that shows this world where half is very dark, sweeping up dark particles from the Phoebe ring, and the other half is very bright, not as bright as Pluto, Sputnik Planum or Planitia or Enceladus, but it's very bright. Well, Pluto has a similar type of thing, where we have Sputnik Planitia being very bright, reflecting about all the radiation that falls on it, and this dark region here where it hardly reflects any radiation. Okay, so what is the connection that New Horizons has made with surface activity and reflectivity? This is a really important point, that this active area of Pluto, the heart, Sputnik Planitia, with the glaciers, is very bright, as is Enceladus with the plumes and the activity that we know exists on Enceladus. It also reflects about 100% of the radiation. So we realized at some point while we were doing this that there's another object in the Kuiper belt that is also very reflective. And this is work that Bruno Siccardi and his team has done, measuring the thermal emission and trying to figure out how large it is. This is Eris. This is the other dwarf planet in the Kuiper belt. Here is an artist's rendition there on the left. Eris and its little companion, Dysnomia. It has a reflectivity from the surface also of about 100%. So what we are saying is, because Enceladus, from Cassini, we know it's very reflective. It looks like it's covered in fresh snow. And Pluto, its active regions are very reflective. We wouldn't be surprised if we went to Eris and saw that it's also active. So this is something we can infer just looking at a pinpoint of light and combine it with our spacecraft observations, that we are pretty, I wouldn't say certain, but we wouldn't be surprised if we saw some type of activity on this other dwarf planet in the Kuiper belt. Thank you. I'm going to turn it over to Alan Stern, who's going to talk about clouds on Pluto.
Thank you, Bonnie. So we move from Pluto's spectacular surface to Pluto's fascinating atmosphere. And clouds, of course, are something that everybody's familiar with. We have them on the Earth. In fact, clouds are common in the atmospheres of our solar system. We see them in the atmospheres of the giant planets, the terrestrial planets, even on planet-sized objects like Titan, that's a large satellite of Saturn. If you look at Venus, you know that it's completely cloud-covered, the Earth less so, and Mars even less so. Titan's clouds are primarily in its polar regions, at least at the current season, where Cassini has been observing. And so it's a natural question whether Pluto, with a nitrogen atmosphere like Titan and like the Earth, but thinner, might have clouds. Now, we've known ever since the flyby that Pluto has haze layers in its atmosphere. This is a beautiful illustration of this. It's an image made by the Ralph instrument aboard New Horizons, just 15 minutes after closest approach, looking back at high phase angle geometry that creates an enhancement in the brightness of suspended particulates like hazes, so that we can more easily detect them. And these haze layers pose a number of mysteries to us. First, they stretch very high into the sky, even above the borderline of this image, more than 500,000 feet, 200 kilometers into the sky. Also, you'll notice there's a large number of concentric layers. We've counted over 24 of them, and that they're organized, beautifully organized, over thousands of kilometers of length scale. And how that happens, we're not sure. But hazes are not clouds. Clouds are defined as discrete opacity structures rather than diffuse ones, and they're optically thick. And these haze layers are only about 25% optically thick in this projected view, and if you were looking up from the surface vertically, where you don't have the slant path advantage, it'd only be about 2%. So what we're looking for when we talk about clouds is something different. Again, discrete features that are optically thick and therefore would block the surface below them. Now, we know from simply being familiar with this beautiful image of Pluto's encounter hemisphere, seen in natural color, that there must be few clouds. In fact, it's largely cloud-free. At least it was in July of 2015 when New Horizons made its exploration. But what we've done on the science team is take a harder look. We've been looking at high-phase imagery, which again is the most sensitive tool that we have in our inventory for looking for these kinds of structures. We've looked at all the LORRI high-resolution images, high-resolution imager images, and the IMVIC images from Ralph that are high phase. We've also looked at low phase, but the only detections that we made are with high phase imagery. And we've created an inventory of candidate cloud features, which I will show you. Now, I have to say, before I show them to you, none of them can be confirmed as clouds because all of them are very low-lying, close to the surface. And we don't, unfortunately, have stereo information on any of these structures to tell us that they're really vertically separated above the surface and not located on the surface. But they're quite suggestive of possible but rare condensation clouds at Pluto. These 7 images illustrate the candidates that we have. They're the bright features. Let me see if I can. I guess we're not making the laser. There it is. So the bright features here and there, and particularly this one that's easy to spot, and these guys, and you can see the others for yourself, are those 7 candidates. They're all similar in that they are, as I said, very low altitude, and they are all similar in that their length scales are measured in kilometers or tens of kilometers. We don't see any decks or banks of clouds. We see individual discrete potential cloud features. Now, when we map these onto the surface, we find something very interesting. All 7 of the features lie near the terminator, meaning that they're either near dawn or dusk. This is the evening terminator over here and the morning over here, and all 7 of these features are near dawn or dusk, which is actually suggestive that they may in fact be clouds, because those are cooler conditions where the condensation process is more likely to occur. Furthermore, Erica Barth, who's here in the audience, is an atmospheric scientist. She works primarily on Titan and Mars. She's at the Southwest Research Institute, has produced some one-dimensional vertical condensation models for Pluto that reveal that, in fact, the most likely place to find condensates to make clouds is down at low altitude, precisely where our candidates lie. Erica's work has also allowed us to constrain the potential composition of these clouds, because she's found that the only constituents in Pluto's atmosphere that are likely to condense are the minor constituents. like hydrogen cyanide and light hydrocarbons like acetylene and ethane, and not the nitrogen that's so abundant, and not the carbon monoxide that's much more abundant in the trace features. The methane is perhaps an intermediate case. But putting all of these facts together, the suggestive features that we see, their coincidence with the terminator, their low altitude, as Erica's model suggests, makes a strong but not airtight case that some, or perhaps many of these features may in fact be clouds. So what are our cloudy conclusions? First, Pluto's atmosphere, while hazy, is almost entirely free of clouds. If all 7 features that we've identified were added together and you compare the surface area of all 7 to the surface area of the disk, it's less than 1%. So you might say that the situation on Pluto is like it is in the western United States, where the skies are not cloudy all day. We have this handful of candidates. As I said, they're all small and isolated. Because we don't have the stereo data, it's a little bit frustrating. And like many aspects of the Pluto system, the first flyby has given us a fantastic taste of what's there in a very dynamic and changing environment, but it's not enough. In order to confirm whether there are clouds, we would have to go back with new instrumentation and be there for a longer period with something like a Pluto orbiter. Thank you. And now Ross will do the next presentation.
All right, so today I'm going to talk to you about landslides on Charon, but not on Pluto. I'm going to talk to you about the landslides that we've discovered on Charon, the farthest from the sun. But of course, the sun doesn't really have anything to do with landslides. Landslides are really about geology and gravity. Now, the title kind of gives it all away. We don't find any on Pluto, big ones. We do see them on Charon. So let me give you just a little bit of an introduction to landslides on the Earth. So here are a couple of different kinds of landslides on the Earth. The image on the left is a small landslide in Haiti. You might actually even call this one an avalanche. The material just kind of fell straight down. It's only about 400 feet across or so, and the tip of the landslide deposit is only about as far from the base of the slope as the slope really is tall, right? The one on the right in Colorado shows this very long landslide deposit, and we call this kind of landslide a long run-out landslide because of this characteristic. Now, you might be thinking that water might have been involved because this looks so much like a flow feature, but water wasn't. This is a dry avalanche or long run-out landslide. So there are many different kinds of landslides that I don't have time to all talk about today, but these long run-out landslides that leave these big deposits are what we're going to be talking about on Charon. Now, that's not to say that Pluto doesn't have landslides, right? Stuff is going downhill on Pluto too, but just not in quite as big of an amount. So on the left, you can see the informally named Elliott crater and a portion there of Virgil Fossae, the big graben there. And we believe that there's material, of course, that's falling downhill, rock falls, avalanches of that nature, but they don't really have a big mass that falls and then flows. The image on the right shows some of these glacial-like flows into Sputnik Planitia. And again, there's a long flow, but it's not fast, and it's not covering a lot of vertical elevation. So let's talk about what we do see on Charon. So this is a map view of the informally named Serenity Chasma on Charon, and this is where all of the long run-out landslides that we've observed on Charon are. The two outermost arrows show landslides that kind of intersect crater topography, and so we don't have great measurements on them. But the inner ones we can characterize very well, both with our high-resolution photography and our very excellent resolution topography. So we will talk about these landslides each as we move forward. The other interesting thing, before I move on, the other interesting thing, of course, is that one might wonder why we only find them in this one place on Charon. Part of that might be observational bias. Of course, we don't have Charon in 360 degrees all around Charon. We only have the encounter hemisphere. There may be other places on Charon where there are these large landslides that we just simply can't see. The other interesting thing about this particular place is that the slopes on this chasma are are steep, which is one of the factors that we need for landslides. This is a perspective view looking westward along Serenity Chasma out into the plains of Vulcan Planum. Let me tell you a few things about the landslide, hopefully that you can see there. So the tip of this south rim there is about 4 miles tall. That's about as tall as Mount Denali in Alaska. But of course, Denali is a single solitary peak. This is part of a ridge that's many tens of kilometers long. The slopes there on that surface are about 30 degrees. And hopefully you can see at the foot of that slope a kind of lobate deposit that actually runs up against the ridge in the middle of the canyon. We can measure the thickness of those deposits and measure how big they are, how voluminous the landslides are, and of course how far they got downstream. And when we do that, we want to take a look at how those are in context with other landslides that we see in the solar system. And in this graph, it's busy, I apologize. The little blue dots are terrestrial landslides, the little red dots are Martian landslides. You see they're kind of grouped. Martian landslides in general run out farther than their terrestrial counterparts. And all the other dots are icy satellites, landslides that we see on icy satellites. And Charon landslides that we've measured are those yellow triangles, and they kind of are typical. So that's good to know. Makes us confident that these are in fact landslides and that they are in character with other icy landslides that we see in the solar system. So in conclusion, landslides have been detected on Charon. They are the first landslides that we have seen in the Kuiper Belt. We wonder whether they will be detected elsewhere on the Kuiper Belt if we go to other places there and see their geology. But of course, to do so requires new missions to the Kuiper Belt to find that out. Thank you very much. And next, Dr. Amanda Zangari will talk to you about where New Horizons is going next.
Hi, today I'm going to discuss work actually done by my colleague, Dr. Susan Benecke of the Planetary Science Institute. Unfortunately, she couldn't make it out to DPS, and so I'll be presenting on 2014 MU69 and how it is a red, cold, classical KBO. So what is 2014? MU69, it is the main post-Pluto Flyby target of NASA's New Horizons mission. We will be approaching it in the fall of 2018, and our closest approach will be around New Year's. We intend to be passing as close as about 3,000 kilometers. MU69 was discovered by the Hubble Space Telescope as part of a dedicated search for a post-Pluto flyby target. It was chosen because it was the most accessible of our potential targets, and we intend to use the extra fuel to use New Horizons to observe approximately a dozen other nearby targets at a distant range. So what is the cold classical belt? When we did our KBO search, we targeted the cold classical belt. And in the Kuiper belt, where Pluto and MU69 are found, is divided into many regions based on the orbits. To give you a bit of an idea about Pluto, Pluto orbits the Sun 2 times for every 3 times Neptune does. It is inclined to the plane of the solar system. Its orbit is tilted, and it is eccentric. That means that Pluto is sometimes closer and further away from the Sun, depending where it is in its orbit. Right now, it's a little closer away than further. The classical belt, by contrast, is defined by objects that are not interacting with Neptune in the way that Pluto is. When I refer to cold, I'm not referring to the temperature of the object. All of the objects out in the Kuiper belt are cold, I can promise you that. Instead, I'm referring to the dynamics of the system. Cold classical objects, they have low eccentricities. Their orbits are very circular. They have low inclinations. They have very small axial tilt, and they have not been interacted with by other objects so much, and so that we believe that they are the primordial remnants of the disk that formed the planets. So let me tell you a bit about the HST program. It was comprised of 22 Hubble Space Telescope orbits, and we looked at 11 objects. For the faintest objects, multiple observations from multiple orbits were combined, and this program was carried out in June of 2015 and then completed in June to July of 2016. And to determine color, we compared the object's brightness in the 606W filter and the 814W filter. This is very analogous to V minus I, if you are familiar with that system. So on to the results, and just to start, I'll explain this chart here. On the x-axis, you see the approximate diameter, which we're using as a stand-in for faintness of the KBO, with smaller and fainter objects to the right. On the y-axis, we have the color, where redder objects are toward the top. And along the chart, there are several dotted lines to give you the idea of approximate colors of other familiar objects. The least red object is the Sun, followed by Pluto, and all the way at the top up there is Mars. And so the gray points are other cold classical KBOs, while the black points are the objects measured by our program with MU69 circled. As you can see, it's the faintest KBO that has a measured color. It is even redder than Pluto, though not quite as red as Mars. And this color determination is the first surface information ever learned about 2014 MU69, and its color indicates that it's likely a member of the cold classical belt, as these colors are very characteristics of these objects. And so, in conclusion, we determined colors for 11 KBOs that will be observed by New Horizons in other ways, and 2014 MU69 is redder than Pluto, adding evidence that it is likely a member of the cold classical belt, thought to be part of the primordial remnant of the Sun's disk. Thank you, and I would like to turn it back over to Con for moderating the question and answer session.
Fantastic, thank you very much. We'll move to the question and answers section of this press brief. We'll take some questions from the floor and then some online and then return to the floor. Please state your name and affiliation and then the question. And Vishnu Avia has the microphone.
Leslie Sage, Nature. Alan, does the modeling show that cloud formation might be seasonal?
Well, that's a very good question, but we don't have the answer to that, Leslie, because the only modeling that's been done so far are just for the present state of the atmosphere, but that's obviously the next step. That's where we would like to go with just that kind of modeling.
And I had a follow-up too. Atmospheric collapse was expected somewhere around now. Has there been any evidence for that happening?
Yeah, let me give a little bit of background for those who aren't as familiar as you are with this phenomena. Pluto's atmosphere is supported in vapor pressure equilibrium, which means that the amount of gas that generates the pressure of the atmosphere at its base is directly coupled to the temperature in an exponential way. So you make it a little bit warmer or cooler, and the pressure changes by a lot. It's very, very sensitive to that. Because Pluto's orbit is a bit elliptical, owing to its position far from the Sun, and has just passed its closest approach, Pluto's been drawing away from the Sun since 1989. And there are a whole series of papers in the literature that predict the rate at which the atmospheric pressure will decrease as the temperature may decrease on the surface. Because that's an exponential response in some models, the decline is quite sudden, and that's called collapse. Unfortunately, the physics are actually a lot more complicated because there are topographic effects, there are brightness effects, and Bonnie showed you how different regions have different reflectivities. There are seasonal effects, as you brought up in the earlier question, and with all those dials on the control panel and more, it's possible to get a whole wide range of answers, including no collapse at all, although I think that that's unlikely. It's clear from the measurements of the pressure in Pluto's atmosphere that we've been getting from ground-based measurements all that time that the collapse has not yet taken place. There are models that indicate that it could be as soon as just a few years from now, and some models, as I said, that indicate that it will decline a factor of 10 but not completely collapse. We really don't know the answer, so future ground-based observations are going to be the key to this, possibly JWST observations as well. And we look forward to really finding out the answer so that we can tune our models to better understand other active planets in the Kuiper Belt, as Bonnie suggested, we may have.
Charles Choi, Space.com. Is there any data or modeling on how long these clouds might last? And I mean, it's a slightly different question from the seasonal effect. And also, is there any, other body in the solar system, I mean, that we know of that might have a similar atmosphere or comparable atmosphere?
Well, those are two very good questions. Let me take the second one first. The most analogous atmosphere to Pluto's is the atmosphere around the planet-sized satellite of Neptune called Triton. Triton is, in fact, a former planet orbiting the sun that was captured into orbit around Neptune. It has a nitrogen atmosphere with similar base pressure to Pluto's. It has complicated seasonal cycles, but for other reasons. And so Triton is the best analog. And in fact, there were some small discrete clouds that were detected by Voyager at Triton. Remind me of your first question? The time variability, how long do they last? It's a great question. The fact that, well, we really don't know the answer to that question, but one might expect that because all of the 7 features that we identify as possible clouds were seen near the terminators, that there are short-lived phenomena near dawn or dusk each day on Pluto, at least in the current atmospheric conditions.
Oh, and how long, just to let people know, how long is a day?
A day on Pluto is equivalent of 6.4 days on the Earth, almost a week.
Emily Lochtawala with the Planetary Society. I've got questions for Bonnie and Alan. For Bonnie, the similarity between the dark band on Pluto and the dark band on Iapetus is really striking, but isn't it true that we think that Phoebe makes that band on Pluto? And so
Totally, good point. Totally different origin. The Cthulhu Regio, which is the dark band, equatorial band on Pluto, which reflects about 8% at the lowest point. We believe that to be primordial. I mean, it may be augmented by dust from the Haze layer or something, but it's basically primordial. Whereas on Iapetus, that dark, and there it's a whole hemisphere. It's not correlated, with the latitude. It's actually the hemisphere that leads the motion of the satellite. It's believed to be dust that is being swept up from the Phoebe ring, as you point out, and it's really, really dark. I mean, that gets down to about 2% reflectivity. So they have different origins, but you see the same type of albedo or reflectivity variations that are telling you something fundamental about the object that you're looking at.
And then for Alan, the clouds that you identified as being happening near dusk and dawn, isn't that an artifact of the viewing geometry? I mean, by definition, if you're looking at a high phase angle image, it's going to be near the terminator no matter what, right? So is it necessary that they happen at dawn and dusk, or could they be at other times of day?
Emily, you make a very good point. And so let me step back and say that there are both necessary and sufficient conditions. And the sufficient conditions for clouds may, in fact, exist in many places on Pluto, but because the forward scattering geometry that we looked at restricts our most sensitive observations to the dawn and dusk terminators, we may have only detected the clouds there because that's where they're most detectable. You're right that they may exist in other places and we just can't see them. That would be another case of we need an orbiter.
Leslie Sage, Nature. So Alan, you've mentioned an orbiter a couple of times. This is for you and David Schurr. you must have some kind of mission profile in mind. And New Horizons, I believe, was the fastest man-made object in the solar system. So how long would it take to get an orbiter out there, presuming that the mission could actually be funded?
Sure. Well, let me start by saying that, we have a decadal survey process, and the next decadal survey is in 5 years. And so and NASA rigorously follows that process. David can add to that. But we're at the very beginning stages in our science team and in the broader science community of starting to talk about what the right follow-ups are in the Kuiper Belt. As Ross mentioned, some advocate missions to other small planets in the Kuiper Belt to look at the diversity of phenomenology that we would see. Some are advocating going back to Pluto to study it in more detail, and it's all extremely early days. In fact, even mission architecture studies have not yet been funded by NASA. But there have been studies that have been done for other reasons, and let me give you just one example. There was recently a study of how you could use NASA's new large launch vehicle, the Space Launch System, the SLS, to fly a Pluto orbiter. And although New Horizons was the fastest spacecraft ever launched, it still took it 9.5 years to cross the solar system 3 billion miles to Pluto. But with the SLS and the use of ion propulsion like the Dawn mission, but powered not by solar rays because those aren't effective this far from the sun, but instead powered by RTGs, so nuclear electric propulsion for braking. That study showed that you could fly an orbiter all the way across the solar system, despite the fact that the orbiter is heavy, given the SLS's great capability, in only 7.5 years.
So just to add a little bit, our general strategy as we've been exploring the solar system is to first fly by, then try to orbit, ultimately land, and even look for mobility roving around on the surface. So the next logical mission to Pluto, when one could be scheduled, would be to put an orbiter. We are starting to look at the studies to support the next decadal survey, and of course this would trade against other very interesting objects in the solar system, including a lot more of the outer planets, which we haven't yet explored. Uranus, Neptune, Tritons, very interesting in comparison. So there's the decadal survey process will try to help set what the priorities will be. But we're starting to look at those type of mission concepts. Clearly, our RPS, radioisotope power systems, are a potential way to enhance the mission and allow us to get there more quickly. And of course, as Alan points out, the SLS becomes a game changer for getting to places in the solar system much faster, including what we're looking at today with the Europa mission, where we can get to Jupiter in 2.5 years.
Emily Lochtwala with a question for Amanda.
Okay.
Can the color of MU69 tell us anything about its albedo and its size, or is there no relationship between color and albedo?
I know that typically objects in the Kuiper Belt of these colors have somewhat dark albedos, but I believe that it can vary.
Do we have any questions online, Rick?
Yes, we do. We have quite a few, actually. We'll
Great.
start with one for Alan from Nancy Atkinson of Universe Today. She asks, what are the candidates for what the clouds are made of? And does potential cloudiness or lack thereof tell you anything new about Pluto's atmosphere?
So the most likely candidates, based upon the modeling that Erica Barth has done, are the following molecules that are known constituents, trace constituents in Pluto's atmosphere. They are ethane, acetylene, those are both light hydrocarbons, and hydrogen cyanide, or HCN. As I said in the presentation, it's also possible that methane can condense in Pluto's lower atmosphere under the right conditions.
Okay, here's a follow-up question on the same topic, also for Alan. This is from Raj Pillai from the Facebook Society of Unapologetic Pluto Huggers. He says he knows you, or you know him. Since the clouds are seen at dawn and dusk and close to the surface, can it possibly be fog? And there you might want to distinguish between what what is the difference between fog and
I
clouds?
will. Thank you. That's a great question. A fog is defined as a cloud at ground level. And since we can't recover the heights of these features, in fact, we can't be certain, and I want to stress that there's a strong circumstantial case that these are clouds, but it's only a circumstantial case. We can't definitively say that these are features above the ground. They certainly could be low-lying. And in fact, if you take a look at several of the cloud candidates, it looks like they occur in what appear to be topographic lows surrounding constructional mountain features on the horizon. So in fact, fogs are also clouds. They just happen to be clouds at ground level, and some or all of these features could be exactly that.
And he also asks if there's any evidence that there's been any precipitation in recent times.
There's no evidence for precipitation on current-day Pluto.
Okay. Here's a question from Kelly Beatty from Sky and Telescope for Bonnie. He says a key discovery at Pluto was finding, CH4 ice. That's methane, right? CH4. He credits that to Dale Cruikshank, I think. If you suspect that Eris has an active surface, what kinds of spectroscopic detections might support that?
Well, I think the important thing about Eris is that it's as bright as Pluto. If you look at the albedo, okay, the global albedo of Pluto is about 0.6 in the visible. But the global albedo of Eris is 1. It's more like Enceladus. So it's just based on the brightness that we would have active. It really doesn't have to do with the composition, because on Enceladus, it's actually water ice that is causing the activity. So it's covered with water, whereas Sputnik, Planitia, is primarily methane ice, and it is unit albedo, 1, it reflects 100% of the radiation. So I think it's more the argument that we're making for the likelihood of activity on Eris is more that it's very bright, not necessarily what the composition is. So I think if it be either methane or water ice, it would still be the same argument that we're making, that it's activity.
Okay, here's a question for Ross from Calico Field of Space.com. She asks, what does the presence of landslides tell you about the composition of the material that slid and the composition of the ground or the cliffs around it? And is there any way to date the landslides?
So it doesn't tell you much about the actual chemical composition of the material. It tells you more about its strength properties. So one of the requirements for a landslide is you have a steepened slope that can then fail. And so to have that, you have to have a material that's strong enough to create a steep enough slope to then fail. And of course, that can be a wide variety of materials. And on Charon, we think that it's the strong, cold water ice that makes up all of the surface that we primarily see there. There was a second question. Could you repeat that?
Is there any way to date
dating.
the landslide?
So if you had enough resolution on top of the landslides, you might be able to attempt to count craters on the top of those landslides. But the scale and the perspective view that I showed you, we just can't resolve small features on the tops of those landslides. So it's difficult to determine their ages from that method alone.
Without an orbiter.
Without an orbiter.
Couldn't resist.
Yeah.
Okay,
Consistent theme there.
I'll keep going until Khan tells me to stop.
Okay, we still have 15 minutes, so let's get a couple more from the web.
Okay, so here's another one from Kelly Beatty from Sky and Telescope. This one's for Amanda. He asks, is there any hope of using Hubble or perhaps a large ground-based telescope to determine the rotation rate of MU-69? And how important is knowing the rotation rate for planning the flyby?
So we would very much like to use Hubble to determine the rotation rate for MU-69. We have not been able to observe it from our astrometric observations as of yet. We also have not been able to see MU-69 from the ground, so we would require the use of the Hubble Space Telescope. As far as planning, we would love to know the rotation rate, and especially because should the object be oblong, we would love to fly by when its broadest side is facing the telescope. And we have some fuel that we could use to adjust the accounter if it's a reasonable amount and we know in time.
And here's another question from Kelly on also about MU-69. He asks, he says, I'm hearing that ALMA the Atacama Large Millimeter Array, can be used for radiometric fits to establish the diameters of Kuiper Belt objects. Is MU69 too small for that?
I would imagine it would be very much near the limits. I know that there was a study discussed earlier at DPS that was hoping to use ALMA to see Dysnomia, Eris's moon, and it was not capable of seeing it because it was so small.
If I can add to that, I think Amanda gave a great answer about ALMA. It is at the hairy edge of what ALMA can do presently, in part because ALMA is not a complete array. By the time it will be complete, we'll almost be there. But in the interim, next summer, there are 3 identified stellar occultation opportunities for MU69. And if those can be observed by ground-based or by NASA's Airborne SOFIA Observatory, we'll either be able to get a chord across the object, which is a lower limit to its size, or if we get multiple traces, we can paint its shape and get a fit to its size. And that's probably the more direct route to get that information before New Horizons arrives.
We only have one more at the moment, Con, so let's do this one.
Do that one.
This is from Daniel Fischer in Germany. He writes for Sky Week. He asks if any of you dare to predict what the topography of MU69 will look like from close up. Might it be more like a comet, like Halley or Churyumov-Gerasimenko, or might it look more like an asteroid?
Anybody want to venture?
I'll predict a more asteroid-like composition. I think it's going to be, being such an old object, I think that we're going to see a very old, hard surface.
Could be anything.
Yeah, well, I don't make predictions because they're so often wrong when we go to new types of objects. And we've never been to anything like MU69, something that's been cold for the entire 4 billion years, and it's in addition small enough to not have the same degree of geological processes that we see on Pluto and Charon that are much more massive objects that have planetary processes on them. And this is a completely new kind of world we're going to. It's somewhere in the vicinity of 10,000 times the mass of Rosetta's comet, and yet only 1,000th the mass of Pluto. So I think we will stand by. January the 1st, 2019 is coming, and New Horizons is going to let you know.
Yeah, I just want to add that I think it is, as Alan said, a new type of object. We've looked at Pluto, which is a large active object. 67P Churyumov-Gerasimenko, the Rosetta comet, is also from the Kuiper Belt, and that's a small primitive object. We think Phoebe, which is a moon of Saturn, is also from the Kuiper Belt. There's good evidence for that. That's smaller than Pluto, and it's not active. It looks like it's been pretty primordial. And we're looking at an additional 4th object that is between the small comets and Phoebe. So we're just kind of filling in the diversity of objects that may exist in the Kuiper Belt.
If I can just add one more thing. In this population called the cold classicals, about 1/3 of the objects have satellites, and that's a lower limit to the satellite frequency because we can only see down to a certain faintness, and we can only see satellites that orbit beyond a certain distance because we're looking from so far away. It's entirely possible that when New Horizons arrives, it will discover 1 or more satellites in orbit around MU69 and have even more objects to study.
And we have a question from the floor.
Charles Choi, Space.com. So it occurred to me, if they're not clouds, what might they be? Frost?
So excellent question. If those features are actually down on the surface, then they're just individual surface units that have particularly reflective high phase properties that are different from the surrounding terrains. Because of their situational location and the other circumstantial evidence that I pointed out, I think that that's the less likely possibility, although we can't rule it out.
Great. I think we have 2 more questions, and then we'll close out.
Okay, here's a follow-up for Ross from Calico Field of Space.com. To clarify, do you know anything more about the state of the water ice in the landslides? Does it look like large, solid chunks, like pieces of an iceberg breaking off, or is it more granular?
Well, we can only imagine, again, because seeing those kinds of details are below the resolution limit of what we can actually see. So we really just kind of see this, we can just resolve this smooth apron and this this deposit as a whole thing. We can't see individual grains or rocks within it, so we can only imagine what that might be like. It's likely, given the very cold conditions on Charon, that it probably, if one could see it, it's probably boulders of ice rock, right? They might have gotten some melting on their edges, kind of got slippery but not completely melted to aid their rush out away from the slope. But that's only a guess based on what we think we know about landslides.
Okay, I have a question probably for Alan. This is coming from Rick Feinberg, AAS press officer. In the early maps of Pluto with the informal names that are on there, you have Sputnik Planum. Now you're referring to it as Sputnik Planitia. I guess the difference is one is a plain and one is a plateau, and I'm wondering whether this was a conscious choice to change the name and what made you change it.
Yeah, so, Sputnik itself is the largest and brightest, most distinct feature on the encounter hemisphere. It forms the western half of the heart, or the region we informally call the heart being called Tombaugh Regio, after Clyde Tombaugh, who discovered Pluto. We could see Sputnik from a distance of over 100 million miles away. And then on the occasion of the encounter, on July the 14th and 15th, when the first high-resolution imagery came to the ground, this feature was so prominent that we knew that we had to identify it with a name, and we had already created within the team a series of name banks, one of them for historic missions of exploration that preceded our exploration of Pluto, which I think was historic. And Sputnik, which was the first Russian satellite, was near the top of our list, and we chose it for this region on Pluto. But the original data that we had, and we were reacting quickly because we only had received this data literally an hour or two before the press conference where we announced it, led us to believe that it was a planum, meaning above the surrounding terrains, more like a mesa of vast scale. Later, as more and more data came to the ground, all of our stereo imaging data sets landed. They were processed. The hard work was done by one of our geology team members named Paul Schenk at the Lunar and Planetary Institute, who definitively determined that, in fact, it's not a plane above the surrounding terrain, but below it. It's in a basin. And therefore, the original interpretation, which was based on the preliminary data available in mid-July of last year, that it was a planum, was incorrect. It's actually more correctly called a planitia, and that's how the evolution of that name took place.
Okay. And a quick question for Ross. What do you anticipate might be causing landslides? Do you think that it would be internal geologic activity like, Charon quakes, or might they be caused by impacts, or is there no way to tell?
Well, from the data that we have, there's no way to tell. It's likely that any activity on Charon was ancient, so even though we can't see craters on the surfaces of these landslides, they probably are pretty old and are concurrent with the timing of the tectonic faults on Charon. So it could have been from earthquakes at that time, but it also could have been from more recent large impacts that set off a seismic trigger, and there was just enough mass just waiting to fail on those steep slopes in Serenity Chasm.
And one more from Kelly Beatty at Sky and Telescope for Alan. He says, Hubble images of Pluto taken about a decade apart show wholesale changes in the locations of albedo features. Is anyone going back to relook at those images in light of the New Horizons results and what those changes might represent?
Boy, I really want to talk about an orbiter for future changes. But actually, the answer to Kelly's question is yes. Mark Bowie, who's on our team and who is the preeminent modeler of Hubble imagery, has a project underway to do exactly that, and I'd encourage Kelly to ring Mark up and have an interview.
All right, I think that largely concludes this press briefing. I do have one announcement for you guys. As you know, European Space Agency's ExoMars Schiaparelli entry, descent, landing demonstrator module is landing on Mars tomorrow morning. So there will be a live stream of that event at 7 a.m. through 8:30 a.m. in Ballroom D of the Pasadena Convention Center across the road. So I encourage you to go to that. For sure.
What time is the actual landing?
That's a good question. Within that time frame. 7:48? Okay, thank you very much, Anita. And then secondly, there's USRA scientists who will be available to talk to the media this afternoon and tomorrow morning about that event, and the list of those who are available is posted at the press office across this center. So I'd like to thank you all for coming to the New Horizons press briefing. Thank you.